Okay, so let's go ahead and analyze the n equals 4 family of n periodics, of 4 periodics. Let's animate that. I'm going to go ahead and draw the outer polygon, which we know is a rectangle. Its vertices move along Monge's orthotic circle, not shown here. Now what I want to represent, let me stop this, is a point M that from which I'm gonna draw perpendiculars to the sides. All right, now I can move this point M around like so, and I can animate my rectangle. Nice. Let's go ahead and draw the polygon that corresponds to that. And let's go ahead and draw the center of mass. First of all, the vertex averages C0 prime, it's stationary, and the area C2 prime. As I increase the aspect ratio here, we can tell that these two guys are basically stationary on the ellipse. Right? Now, the really neat result is the following. When I place M at a focus, either focus, right? If it's on the center, both centers of mass are going to be congruent, they're going to coincide with the center of the billiard, so that's not so interesting. What's interesting is if I place it on F1 or F2, I get a very interesting property. The centroids, the vertex centroid is halfway between the focus of the ellipse and its center. C0 is right here at 0.5, where 1 unit would be the focal length. Whereas C2, the center of the region, is at 1/3, and that's just a neat result. Now you get stationarity. If I go to n equals 6, they distribute themselves slightly different. Okay, I'm still at the focus here. The vertex centroid is still on the major axis, as is the area centroid, but I don't immediately recognize what these numbers are. And there they are, they're stationary. If I go to n equals 8, this might be more harmonious. Not necessarily, they're still there and stationary. Okay, now of course for any even m, if I move even n, if I move m around, I get the stationarity property. So here's n equals 8, here's n equals 6, stationary, and so forth and so on. This is pretty nice.